Welcome to the second lecture, and in this lecture I'm going to go through the idea of what a structure is, and I'm going to make a lean structure, and then I'm going to prove that equivalence relations are the same as partitions. But it occurred to me that before I started, so I'm going to be working in this example lean project. I could maybe, like if you do this lean project, I'm just typing in the chat, lean project install, lean project get ImperialCollegeLondon example lean projects. There, let's put that in quotes. Oh, why do we put it in quotes? So there we go. That's the repo I'm working on. Right, so I'm working on a basic repository that contains some little problems. There's a bunch of, it's the one I was talking about last time, so sort of first year undergraduate stuff. There are things like analysis, equivalence relations, graph theory, group int, and nat. But I thought it was probably worth saying before I start that there are several other projects like this. For example, these ones here that I linked to. The complex number game has some very simple problems about the complex numbers. This has some harder problems about commutative algebra. I'm halfway through a proof of the Nullstellensatz in that project. This is building group theory from scratch. This is playing around with Galois theory. We managed to get splitting fields today, so that's ticking along. And this is condensed sets. I mean, this is something that Schultz has been doing recently that I was experimenting with. But today, let's talk about equivalence relations. So here's this equivalence relations partitions thing. I'm gonna work through the proofs in here. But before we start, let's just do structure examples. There. So what's a structure? So in lean, a structure is things like groups are a structure. So I mean, one could make groups like this, I guess. So here's a structure. So I guess if G is a type, then a group structure on G would be, well, first of all, I guess I'm going to assume that G has got a multiplication and that G has got an identity, has one G, and I'm going to assume that G has got inverses there. And so now I could make the structure of a group on G, and that would be writing down the axioms, Mullersock. And that says for all A, B, and C in G, A times B times C, A times B times C equals A times B times C. And now I have a problem. Invalid structure identifier. Oh, I didn't give it a name. Invalid structure group. Let's call it a group. There. It's got associativity and then whatever, one mul. That says that for all A in G, 1 times A is A. And mul 1. You know, if you think that the axioms for a group involve both mul 1 and mul 1. 1 for all A in G. I mean, who knows what the axioms of a group are? A times 1 is A. And then I guess we need mul left in. That says for all A in G, A inverse times A is 1. There. So I've just defined a group in lean, and so what's going on with this structure? This structure has a name, which is group, and this particular structure takes an input because I didn't want the set to be part of the structure, and it also takes these inputs here. I didn't want the multiplication and the 1 and the inverse to be part of the structure. It's just convenient if we have those already, because then we can use this funky notation here. You see, I can. This star notation here has mul dot mul. It's, you know, G already has a multiplication and a 1 and an inverse right from the get-go. right from the start. So there's the definition of a group. And one can, I mean, here's a structure, here's a silly structure. And so this isn't going to have any inputs at all. To make a silly structure, we're going to need an integer. And that's going to be an integer. And we're going to need, I don't know, a natural number. There. Oops. So now I've made a silly structure. So in fact, let's get, I mean, this structure is quite complicated. Let's do an easy structure. Here's an easy structure, and it's called the silly structure. And to make a term of type silly, so we could check silly. It's going to be a type, I suspect. There you go. Silly is a type, as we see on the right there. And now, how do I make a term of type silly? So silly is a type, i.e. silly is a type. So that means it'll have terms. So how to make a term of type silly? I guess I would do it like this. Example. Let's make a term of type silly. Let's define x to be a term of type silly. And how am I going to make it? So you see, everything makes sense. That's great. You know, everything is syntactically correct. But how do I make a term of type silly? Well, what I have to do is, of course, I have to tell it what the integer is. Maybe this should be called sillyint and sillynat, just to be clear there. To make a term of type silly, I have to give a sillyint, and that could be, I don't know, 7, and a sillynat, and that could be 37. And there you go, everything's compiled. You see, we've got no warnings and no errors down here. We've got one informational, there, we've got this thing here. If I comment this out, there we go. Then there's no warnings and no errors and no info, there's no anything. And I could make another term as well, right? Let's define y silly, and that could all, you know, the sillyint could be 0. There, the sillynat could be, I don't know, could be 1. So there we go. And so now I've made two silly things. I've made, one's called x and one's called y. Whatever. And now we could try and prove that x isn't y, right? There. And if we could manage to prove this, then we could say that we're getting the hang of structures. So they're clearly not equal, because I made one. You know, if you like, a term of type silly is just a pair, right? Silly is really the same. Well, you know, I should maybe say, perhaps I should say the same. Silly is an implementation. Implementation of right. Silly is an implementation of the product type Z cross nat. You see, but Z cross nat is another implementation of this. There. So let's get back to that in a second. Let me see if we can prove that x isn't equal to y. You see, what I was saying here is to give a term of type silly is just to give an integer and a natural number. So we need to take x and y apart to prove that they're not equal. So maybe we could do cases x. What would happen with that? There we go. Oh, that didn't go so well. What should I do here? Maybe I should unfold x. Oh, there we go. That's done well. And I'm going to unfold y. There, because x and y are definitions. So I've now unfolded them. I'm going to turn off my sound so we don't get bleeps all the way through. I've now unfolded them, and now you can see what the goal is here. I've got to prove that this silly thing, which is made out of a 7 and a 37, is not equal to this silly thing that's made out of a 0 and a 1. So maybe the simplifier will do it. Let's try the simplifier. Oh, okay. I see. The simplifier has reduced it. You see, that's the same question, right? This looks a bit complicated. But the simplifier just says, come on, what this actually boils down to is we've got to prove that 7 equals 0 and 37 equals 1. We've got to prove that that's not true, right? And so, how are we going to prove that? Well, let's assume it is true. Let's prove it by contradiction. Intro H. There we go. So now I've got my hypotheses, which are that 7 equals 0 and that 37 equals 1. Maybe I could do cases H. Cases H with H1 and H2. I'm just playing, right? There's lots of ways of doing this very simply. So now I've got, and I guess Linarith will do this, right? Oh, except I didn't import it. Let's import the tactics. There. So, oh, there we go. Oh, that's interesting. Oh, there we go. I have goals accomplished. So I seem to have won already. What happened there then? Unfolded X and Y. Then I run the simplifier. Ah, I see. The simplifier did something different. Let's start again here. The simplifier has now said that we've got to prove that if 7 equals 0, then 37 equals 1. The behavior of the simplifier changed because I imported something. And how could we term mode that one? Okay, I'll give you a term mode proof in a minute. So now let's intro H. Now H says that 7 equals 0. Yeah, I think that Linarith should already do this, right? There you go. Linarith has done it. How can we term mode this proof? Well, unfold X and unfold Y don't do anything, right? This is still true by definition. So we could do, what we really need is we need an extensionality lemma, don't we? Well, we need, yeah, you see, the problem with this structure, is we don't have an extensionality lemma. Let's try this. Let's do that. So let's tell the structure. Let's remove this first. I think this might be instructional. So there's the definition of the structure. And one question that one could ask immediately after making this definition, one question you could ask is that what exactly does lean know about this silly structure? So let's print prefix silly. And let's see what lean has to say. So lean already knows a ton of stuff about silly. And most of these things were written by a computer. Some of these things, there you go, there's an important thing. There's a function here, right? Let's pull out the things which are going to be useful. There's this silly.sillyint, which is a map from silly to the integers. And there's probably silly.sillynat as well. There is. There's silly.sillynat. And what else is there that's going to be of use to us? Silly is a type, yes, fair enough. And there's silly.muck. That's always useful to have, isn't it? There. Silly.muck. That says that given an integer and a natural, I can make a term of type silly, right? And all of the, there's silly.rec. There's silly.rec. And silly.rec is probably useful to computer scientists. Let's not. There's silly.rec. Useful for induction. That will let us do induction on silly. And this group is now broken there because the moment I import tactic, we already have leans groups, and we don't really want leans groups. So those are some things, and in fact we're using them here, right? We use silly.muck. We could do it like this, right? Silly.muck 737. There. That's exactly the same definition of silly, right? And you see this proof still works. If I unfold it, and you can see if I unfold X, I still get exactly there. I've defined this term of type silly in a completely different way, but it's still, the int is 7 and the nat is 37. But I'm lazy, so let me do this there. And now I think, So if I tell Lean to make some more, this says make some more useful lemmas for me, and I'm rather hoping that there'll be an extensionality lemma. Will there? Oh, there we go. Look, we've got these as well. Let's copy. Let's have a look at these. There. So these are going to be really useful, right? Because these say practical things about my type. You see this one here, silly.ext, says if the x and y have got the same, if they're made out of the same integer and the same natural, then they're equal. And xdif says that two terms of type silly are equal if and only if they have this, they're made out of the same integer and the same natural. So how would I do this in term mode? I would say, I mean, let's do this in term mode. We've got unfold x and unfold y, and let's get rid of this. We don't really want to see that anymore. There we go. And we could do intro h there, and so now we have this false hypothesis that these two things are equal. And now I can probably rewrite xdiff at h. Oh, I need to go into the silly namespace. Let's do silly.xdiff at h. And now if I definitionally simplify, let's see what h really says. So this is something that I meant to actually mention with structures. Look at this. If I rewrite this, this is supposed to be useful, right? This extensionality lemma. Extensionality means that two things are equal if and only if they're made up of the same parts. So we've got these things here. This is x and this is y. And if x equals y, then they should be made of the same parts. So if I apply this, if I use this extensionality lemma, then this should simplify to 7 equals 0 and 37 equals 1. But when I actually rewrite it, I get this mess here, because this says, let's make a silly thing out of an integer and a natural, and then let's look at what the integer part is. You see this mess here, it says, take the silly thing, which is made from an integer, which is 7, and a natural, which is 37, and then let's look at the integer. So that thing there is by definition equal to 7. And similarly, this thing here is by definition equal to 0, right? So this definitional simplification makes things much easier. And so I don't know. So I guess now if I do cases on h, then I'll be able to do linearith. There you go. You see, because linearith just solves this kind of, linearith is the correct tactic to solve this sort of thing. I guess actually maybe who knows. So I should now be able to do this. I should now be able to do this in the, right, here's the answer. Here's how to do this in term mode. Example, if x doesn't equal y. And this would be, let's lambda h underscore. So this says, so I'm trying to prove that x isn't y, so I assume that x is y, and now we have to prove false, right? You see, this is, I don't really, this is not much fun to do in term mode. I'm not really sure I can do this in term. I mean, maybe by simp xy. Does that work? That doesn't work. Hard luck. Silly.xdiff. Yeah, I don't really want to do this in term mode, is the answer to your question. I think this seems to be much nicer in tactic mode. Although I could probably get rid of the unfolding. What about this? There. And now I'm just trying to work out I. What about if I do this? There. What? Hard luck. Okay, I'm going to do simp xy at star. Yeah, I don't want to do this in I don't want to do this in term mode, is the answer to your question. let's get back to the let's have a look at what we're going to prove today. So what we're going to prove today is so here's my definition of a structure. So let's take a careful look at this structure. So this structure is the structure of partitions on a type, right? A type is just a set. So X is a set, except X is a type because we're doing type theory. And I'm going to define the structure of partitions of X. And a partition of X is going to be a set, so it's going to be a collection of subsets of X, and then 3 axioms. And the axioms are every element of the collection is non-empty. Every element in X, it's in one of the what are these subsets called? It's in a subset which is in the partition. Let me call these. Yeah, I need a name for the subsets of this, for the subsets in a partition. The partition subsets. Every X is in one of the partition subsets. If I've got 2 partition subsets and they're not empty, sorry, and their intersection is not empty, then they're equal. So there's the that's the definition of a partition. It's, you know, it's if you like, we're breaking X up into disjoint non-empty subsets. And here's the definition of an equivalence class for a binary relation. I've got a binary relation here. This takes 2 elements of X and returns a true-false statement. So given a binary relation and an element of X, I'll define the equivalence class to be the other things in X, the Y in X, such that R is related, so that X is related to Y. And so I should now prove that if I've got a binary relation which is an equivalence relation, and I've got an element of X, then X is in its own equivalence class. So let's start by proving that. Why is X in its own equivalence class? Well, I guess I should rewrite. Equivalent. I mean, what does this even say? Right? Unfold equivalence class. Let's see what the question is. The question is, I've got to prove that X is in the set of Y such that R is related to Y, and I can probably definitionally simplify this. Yeah, you see there. If you think about it, what does it mean? What's the definition of X is in this set? X is in the set of things with a property. What does it mean to be an element of these things here with this property? It means that you have the property, right? So X is an element of this set here, of the Y such that Rxy. That just literally means Rxx, right? And so Rxx, I guess, why is that true? I see, I know that R is an equivalence relation. Is equivalence relation a class? No, it's not. So why would this be true? I guess I could do cases. I could do R. Look at this. I could do R cases, HR, with RST there. And now R is a proof that capital R is reflexive. S is a proof that capital R is symmetric, and T is a proof that capital R is transitive. And so this is, I guess this is exactly the statement Rx, right? There we go. So there's the proof of that. Because I mean, I could even unfold reflexive just to show you what's going on at R. And we can see that R is really a proof of the assertion that for every element of X, X is related to itself. So there you go. And of course we can get rid of these things here. They don't change the goal up to equivalence, right? We could just probably get rid of everything. All the unfolds. There you go. This would be nice to do. This would be nice to do in turn mode. This would be nice to do in turn mode. My guess is that, so you see, instead of R is some, this HR, this equivalence is made up. To make a term of type equivalence R, you need 3 things. You need a proof of reflexivity, proof of symmetry, and proof of transitivity. The subsets are called blocks. Thanks for that. Thanks for that, Esmerel. I wonder if you're the Esmerel that I know. So this is, HR is made up of 3 things: reflexivity, symmetry, and transitivity. And we can just get to it. Look, we can just get to, if I do HR.1, we can directly access those 3 things. Let's get rid of this. Now you see, we can access those 3 things by just saying that HR.1 is the first one. So HR.1 is a proof of, HR.1 is a proof that this relationship capital R is a reflexive relation. So now we can get rid of everything, and now our proof is just, now we don't even need this. The proof of this is this, hr.1x. There you go. Maybe August would like that better. Hi, hi Sophie. So that's the proof. That's the proof that every element is in its own equivalence class. So now we're going to prove this equivalent. Right, now we're going to prove this equivalence here. Before we start on this, let's have a look at what this statement. So here's this example. This is the main thing I'm going to prove today. If I get around to finishing it, I'll probably accelerate as things go on. So what have we got to prove here? So X is a set, or I mean, we're doing type theory, so X is a type, but really X is a set. I mean, if you're used to set theoretic mathematics. And this example here claims that there's a bijection between the set of equivalent, well, the type of equivalence relations on X and the type of partitions on X. And it says that those two types here, the type of equivalence relations on X and the type of partitions in X, it says that they're related by this funny little symbol here. And this funny little symbol here, annoyingly, is called equiv, right? And so you might think that equiv has got something to do with equivalence relations, but actually it doesn't. Equivalence relations are called equivalence in lean, and equiv is a different thing. Let me just go, let's go to this definition of equiv. I can't find the definition. Go to definition. Oh, here we are, great. There. This is the definition of equiv, not to be confused with equivalence relations. An equiv between A and B, between two types alpha and beta, an equiv between two types alpha and beta is the following things. You see, it's another structure, so I thought it would be kind of cool to look at. It's another structure. To give an equiv from alpha to beta is to give a function from alpha to beta, a function from beta to alpha, and then a proof that if you do the inverse, so these functions are called inverse functions. Yeah, let's call them f and g, right? To give a term of this type is to give a function f from alpha to beta, a function g from beta to alpha, and then a proof that g is the left inverse of f, and a proof that g is the right inverse of f. So in other words, it's to give two functions, one from alpha to beta, one from beta to alpha, and then the proof that they're inverse bijections. So that's what this type is here, this equiv. And the notation for equiv is this funny little, not quite an isomorphism symbol. So what's going on here? We're trying to prove that the set of all equivalence relations on X bijects with the set of all partitions on X. That's, you know, that in set theoretic language, that's what this says. The set of all equivalence relations on X bijects with the set of partitions of X. And this is slightly stronger because it's not just the abstract statement that they're a bijection. It's you know, this statement contains data. We actually have to give the bijections. So to construct a term of this type, a term of this equiv, let's go back to this equiv. If I want to construct a term of type equiv alpha beta, it's not good enough to abstractly prove that there exists a bijection between alpha and beta. We actually have to give the data, we have to give the function, and we have to give the inverse function, and then prove that they're inverse bijections. So that's how we're starting here. We have to actually give the function, which given an equivalence relation, which is this R, we have to come up with a partition. And here it is. So now you can see, there, look, my job now, you can see what's going on here, there. What's happening here is that R is an equivalence relation, and we need to now make a partition there. And so that means we open these squiggly brackets, and then we have to say what C is. Well, let's have a look at what is a partition. It's this collection of blocks, and then it's the proof that every block is not empty, that the blocks cover X, and that the intersection of two, if the intersection of two blocks is not empty, then those are the same block. So we're going to let the box be the equivalence classes, right? The box is going to be the subsets of X. This set X is really badly named. This set X, a term of type set X is a subset of X. So the blocks are going to be the subsets of X with the property that there exists an element of X such that this subset happens to be the equivalence class. So now what have we got to do here? we've got to prove some theorems, right? And this first theorem here, we've got to prove that for every, let's see what we've got to do. We've got to prove that every subset, which is an equivalence class, is non-empty. So let's do intro, what are these blocks? Let's call B, okay, B is going to be a block. So intro B for a block. And now let's assume that B, and now let's do this cleverly. Let's look, and we can intro HB, and HB is now the proof, and HB is now a very long-winded proof that HB is the equivalence class of X for some X. We can do all this. We can do all this. Let's do all this. Look, let's just use rintro. Rintro B, comma HB. There. We can do all this in one line. Oh no, we can't. Because I haven't got a comma. There. Oh, we still can't. Let's try it like this. Let's try B and HB. What about that? Oh, this looks good. So now HB is a proof that B is in the set of subsets of X such that there exists a little x such that S is that equivalence class. So I really would I want the X straight away, right? X comma HX. There. And now in fact I don't need B. I don't need B at all because B, I'm just going to define B. I'm going to define B to be the equivalence class. I'm just doing nothing mathematically here, right? There. This fancy little lean line, you see, this is what we have to prove, right? This is what we had to get to. The goal is now the statement that if little x is in big X, then its equivalence class is non-empty, okay? So that's what a mathematician would say straight away. What's the first problem? We have to prove that every equivalence class is non-empty. So let's prove that this equivalence class is non-empty. To prove that something's non-empty, we need to exhibit an element. So let's just use X. And that hasn't worked. That's rotten luck. Oh dear. Because the definition of is not equal to the empty set. Any empty. Look, there we go. So instead of proving it's not equal to the empty set, let's prove it's non-empty, right? Because if you think about it, those are slightly different things. So now let's use X. Bingo. So now we have to prove that X is in the equivalence class of X. I should maybe say what this little up arrow is. This R, I said that R was an equivalence relation, but that's a lie. R is a term of this type. So R is actually a pair. R is actually a pair consisting of a binary relation and a proof that it's an equivalence relation. So that's what this little up arrow means. This little up arrow here is, yes, we know it's a binary relation which happens to be an equivalence relation. But let's just work with the fact, up R is the proof that it's an equivalence relation. So we've proved this already. Why is X in the equivalence class of X? This is we've proved it. It's mem class. It's exact mem class X or something. Exact mem class something X. Rx. What about that? Doesn't like it. What have I done wrong? R.2. How about that? There we go. You see, this is because R is in fact R is two things, right? R is a binary relation and a proof it's an equivalence relation. And the binary relation is R.1, and the proof that it's an equivalence relation is R.2. So there's the proof of non-empty. Right, let's get on. How are we going to prove that these things cover? What does this even say? Okay, so this, we've now got to prove that the blocks cover. So let's let little x be arbitrary, and now we've got to prove that there's a block. We've got to prove that there's a block which X is in. So again, this is going to be, let's use the equivalence class. Let's use equivalence class Rx. Great. So now we should have to prove something obvious here. So now we've got to prove that this equivalence class is in some set. Okay, we've got to prove that this equivalence class. Let's simplify this. Let's see what actually is going on. Let's definitionally simplify what we actually have to prove. Okay, so what we have to prove is two things. Firstly, we need to prove that there exists some y in X such that the equivalence class of X is the equivalence class of y. Right, well, I think that's pretty easy. We're going to use x there, and that has done it. And so now we have to prove that x is in the equivalence class of x. Oh, we have this already, right? We have to prove that x is in the equivalence class of x, and that keeps coming up. There we go. So that's proof that they cover. And now unique. Now this is going to be harder. So how are we going to prove this? So let's take two blocks, intro B1 and B2, intros them. Let's take two blocks, and what do we know? Ah, I see. So intro HB1. That's just, HB1 is the, you see, this is exactly, we don't need names for this. We don't need names for these blocks. Let's assume, because we know that these blocks are blocks. So let's intro x.ruffle. Let's say that the first block is the equivalence class of x. And let's say the second block is the equivalence class of y. So now our goal, there we go. So now we have something to do. So now the equivalence class of x, we now need to prove that if the equivalence class of x and the equivalence class of y are non-empty, the intersection is non-empty, then we have to prove that they're equal, right? That's exactly what we need to do. So let's assume that our the intersection is non-empty. And now, of course, we know that if I should never have done this. My definition of partition is lousy. I should have said, instead of saying that the intersection is not equal to the empty set, I should say that the intersection is non-empty. So now we can do cases on this, right? We know that we have this hypothesis says that this intersection is non-empty. So with z, hz, right? So now what have we got here? Great. So now we have x, y, and z. Oh, this is a bug. This bug's been fixed, but I didn't update. Rotten luck. We have x, y, and z, the elements of capital X. And we now have this hypothesis that z is in the equivalence class of x and z is in the equivalence class of y. And I now need to prove that the equivalence class of x equals the equivalence class of y. And I feel like we need a lemma, right? We should have proved. I think here's a nice lemma. Here's a lemma. Let's have. These should be variables. Let x be a set and let R be an equivalence relation on x. Right. Here's a lemma. It says that if an equivalence class is a subset of another equivalence class. No, what does it say? This is what we need. We need that if x is related to y, we need this, don't we? If x and y are in x, and then if x is related to y, rxy, then I want to deduce that the equivalence class of x is a sub. What's the easy way? I think we need to deduce that the equivalence class of x, equivalence class of x is a subset of the equivalence class of y. Is that the, no, I think we should, it's this, right? The equivalence class of y is a subset of the equivalence class of x. I think this would be a cool intermediate lemma. Rx. So let's prove that. Oh, it hasn't got a name. This should be called, I don't know, subset of rel. There. If x and y are related, then the equivalence class of y is a subset of the equivalence. So how are we going to prove that? What does it mean for a set to be a subset of another set? Let's get rid of all this junk here. What does it mean for a set to be a subset of another set? It means every element of this set is in this set, right? So let's let z be an element of x, and let's let 8z be the statement that z is in the equivalence class of y. Remember that. What does that actually say, right? Z is in the equivalence class of y. Just says we could actually make it say. I mean, we could unfold. I mean, we could just. This just says that. What does it say? It says that r is. It says that y is related to z, right? There. That's what that actually says. You see, I've just changed it. hz says that y is related to z. And the goal here, the goal is just that x is related to, right? So change rxz, right? That's really what we're trying to prove. So we know rxy, we know ryz, and so we want to apply rxz. Sorry, we want to deduce rxz. So that's by transitivity, right? Oh, so this lemma isn't true, ha ha ha, because I never assumed that the relation was an equivalence relation. So let's add in the assumption that the relation is an equivalence relation there. And so now now that's going to be apply hr.2.1, right? There we go. So hr.1 is a proof that it's reflexive. hr.2 is the proof that it's symmetric and transitive. So I've implied the wrong thing. So hr.2.2, that's the proof that it's transitive. In fact, why don't I just, it's exact, we can do this, right? This is exactly the assertion that it's transitive applied to hxy and something. And that something is 8z. There we go. So there's a proof. There's a proof that if x is related to y, then the equivalence class of y is a subset of the equivalence class of x. That's just a useful thing to have. Oh, now I've broken this proof. What have I done? Oh, I see. I need to insert. Oh dear, I've broken my proof. That's a bit annoying. Is it r.1? There we go. Right, we're back. There. So now what? We're now trying to prove IC. Right. We're trying to prove, we know that, what do we know here? Let's do cases xz with hzx, hzy. We know that z is in both equivalent. You see now z was in the intersection. Here we know that z is in the intersection of these two equivalence classes. It's in the equivalence class of x and the equivalence class of y. And so that just literally means that it's in both of them. There. So z is in the equivalence class of x. And this now just says, what does this just say? This just says change r xz at hzx, right? At hzx. It says r.2. Oh, it doesn't. What have I done? r.1? r.1, of course. And so that's lousy. I should have called this hxz. Let's call this hxz, and let's call this hyz. There. Change r.1x, and similarly we can. Let's have a look and see what we've got. Yz at hyz. Let's see what this question actually says. So we know that x is related to z, and we know that y is related to z, and we want to prove that these equivalence classes are the same. And of course, two sets are equal if and only if they're contained in one another. So I could apply, what's that going to be called? LE antisim, or subset antisim or something. The subset relation is antisymmetric. No? Yes. If I apply the theorem that says the subset relation is antisymmetric, you see there it says there, A is a subset of B and B is a subset of A implies A equals B. Then we now have two goals. We've got to prove that the equivalence class of X is a subset of the equivalence class of Y, and the equivalence class of Y is a subset of the equivalence class of X. So the next, the next thing we need to do is to apply our lemma, right? So now we need to apply subset of rel. Apply subset of rel. And now we need the proof that it's an equivalence relation. Hard luck. R.1. Let's try that. There we go. Great. So now we have two problems. Our first problem is we know that x is related to z and y is related to z. We need to prove that y is related to x. And now we have x related to z and y is related to z. We need to prove that x is related to y. So now this should all just follow from symmetry, right? We should do cases r.2. Let's do cases r.2 with reflexive, symmetric, and transitive. Let's just actually get these things. Reflexive, symmetric, and transitive. There. Let's do our cases on this. Great. So now we actually have names for these two things. So now how are we going to prove this? So how are we going to prove that R is related to X? I see. So this one we should apply transitivity. Applied tra. And now we've got to prove that R is related to something. Why don't we apply? Yeah, you see, this is we want to prove that R is related to X. I want to deduce it from transitivity. Why don't we apply transitivity? Takes in a proof that R is related to something, and the proof that that something is related to X, and spits out a proof that R is related to X. So we already have a proof that R is related to Z. So why don't I just feed that in? H, Y, Z. There. We're just working on the top goal here. Now I've got to prove that Z is related to X, and I know that. I see. So this is exact sim HZX, right? There. That's HXZ. Sorry. That should have done the first one, and now this second one, I'm going to prove that X is related to Y, and so again, this time I'll use transitivity. I'll apply transitivity and the fact that I know I know the fact that X is related to Z, and so it suffices to prove that Z is related to Y, and so again that's symmetry, symmetry X, H, Y, Z. Oh, I spelled exact wrong. Let's try. I've still spelled it wrong. And it's X is related to Z. No, what have I done? I've still spelled exact wrong. That's the problem. Exact sim something. I'm supposed to be proving it's X, Y. There we go. So there's the proof of that. And that means we've actually defined the function, right? So we defined the function in one direction. And now this function here, this is the function in the other direction. So now given a partition, we need to come up with an equivalence relation. And my equivalence relation is the following. We take two elements X and Y, and the equivalence relation is simply that there exists a block such that X is in the block and Y is in the same block. So that's the definition of the binary relation. And now, of course, we've got to prove it's an equivalence relation. So we can see the first goal here is we've got to prove that for all X, there exists a block such that X is in the block and X is in the block. So again, so let's let X be an arbitrary. Let's let X. So this is kind of interesting, right? It's kind of obvious that this is an equivalence relation. So Lean is demanding that we prove it's an equivalence relation. So we have to prove that. Now we have to prove that there exists a block. So let's use. Why don't we use the equivalence class? That's a good idea. Why don't we use the equivalence class of X? That would be a good block to use. Oh, it doesn't like it. Oh, because I need to tell you what the equivalence relation is. What is the equivalence relation? No, why? Oh, we can't. Curses. We can't use. I've got this wrong. I've got the logic wrong. We can't use the equivalence class of X because we don't have an equivalence relation. You see, like if I was given a lecture, I would have made a mistake there, right? But Lean is keeping me honest. So I need to find. Ooh, right. I need to find a block that contains X. That's one of the axioms, right? There, H cover. I need to use H cover here. So why don't I use H cover? How about that? No, Lean doesn't like that either. So what does H cover say? Oh, I see. It's because I didn't say it's P.H cover. What about that? Doesn't like that either. P.H cover. P is a partition of X. So P.H cover should be. Oh, I see. We need to. That just says that something exists, right? Let's do this. The problem with P.H cover. Yeah, let's not do this. This is a cute way to do it, but let's not do it like this. Let's do cases on this. P.H cover X says that that there exists a block with block H block, right? This statement here, this assumption about this partition says that you can see what it says, right? Oh, no, we can't. Yeah, there exists a set, which is, what does it say? It says that there exists a set which is in the partition and something else. HX probably. Great. So B is the set. HB is the proof that it's in the that it's a block. HX is the proof that X is in the block. And so now what are we going to use for our set? So we're now going to use B. And we now have to prove that B is in, we now have to prove HB. We could just use HB, right? We now have to prove that B is a block, and that's the proof of this. And so now we have to prove that X is in B and X is in B. And we know that X is in B, and so I guess that some tactic will do that, right? So there we go. There. The congruence closure tactic proves that trivial thing. So now we've got to prove it's symmetric. Oh, this is kind of cool. I guess proving it's reflexive, symmetric, and transitive might take us to the end. Who knows? I'm going to prove it's, what have I got to prove? Oh, let's go here. I've got to prove that for every, I've got to prove it's symmetric. So let's intros X and Y there. And so I've now got to prove IC. I've now got to prove that if there exists a block such that X is in the block and Y is in the block, then there exists a block such that Y is in the block and X is in the block, which is kind of obvious. But when you think about it, actually, I wonder if we could, because it is obvious, I wonder if I could just get a tactic to do it. Yeah, there you go. You see, it was obvious, right? You just follow your nose to prove that. And so there you go. That's kind of, you see, lean has a certain amount of artificial intelligence. So now what's going on here? We need to prove transitivity. So let's let X and Y, intros X and Y and Z. You see that somehow that's just a, this is a proof. You see what I'm doing is I'm working very slowly because this is supposed to be instructional, but I'm just getting lazy because I did want to show, there's one more thing I want to show you. So now there exists, now you see the automation won't do this. This says, let's assume rintro, let's assume that there's an XY block. So this is the XY block, and this is HBXY. And let's just leave it at that to see what we have so far. So we're trying to assume transitivity, and remember the definition of the relation is there exists something that's in both of them, right? Oh. Yeah, okay. Let's see what this does. You see, we can do more, right? This is the hypothesis that it's a block, and this is the hypothesis. Oh, let's just call this block B. There, HBX, HBY. We're still trying to state the question, right? So we're still trying to work out what it means for this thing to be transitive. So let little x, little y, and little z be in capital X. And let's assume that there exists a block such that X and Y are in that block. Great. And let's assume that there exists a block, I don't know, there exists a block C such that Y and Z are in that block. Oh, HCY and HCZ, of course. There. And now I've got to prove, let's see what I've got to prove. Can I get away with that? I can't get away with that. Curses. I'm paying for my cheap tidy proof. Now I've got to prove that there exists an E. I've got to prove that there exists a block such that X is in the block and Z is in the block. I see. So I've got a block B with X and Y in B, and I've got a block C with Y and Z in C, and I need to come up now with a block. I'm going to use B, right? Use B. I'm going to use B, and there's a proof that B is a block. So now we have to prove that X is in the block and Z is in the block, and we know already that X is in the block, right? So we can use HBX. That's a proof. That's a proof that X is in the block. But now here's the hard part. We need to prove that Z is in the block. We need to prove that Z is in B. And what we have is we have a proof that Z is in C, right? But because Y is in B and C, we know that B and C intersect. And so actually, we have this proof that Z is in C. I'm just going to use that proof anyway, right? We have a proof that Z is in C. We want a proof that Z is in B. And I claim that the proof that Z is in C will do. So let's convert HCZ. There. I claim that HCZ is actually a proof of what we want. And Lee says, hold your horses. you've got to now prove that B equals C. And now I'm hoping that we've got some other axiom. Where are my axioms? Oh, this broke. Oh, why does this broke? Why do I have an error? I shouldn't have an error. Oh, it's because I haven't finished proving this. Oh, I've got an error here. I don't like errors. Let's put that sorry back in. Great. Now we have no errors. Now what's my definition of... We still have an error. What have I done? What's my error? There's an error somewhere. AWA. My proof is broken. Let's not worry. I've broken something. Oh, there's some issue about I have too many x's. Let's not worry about this error. Let's go back to my proof. Where's my proof? Here's my proof. I'm trying to prove that B equals C. And I think somewhere, there we go. Here, you see, I've got this unique thing there. Let's use this uniqueness. So let's apply H unique. What was it called? Let's apply partition. Let's apply P.H unique. There. Now, what does the goal become if we do that? So now we have to do several things. First of all, we need to prove that B is a block. We have a proof of that already, actually. So we could do HB here, probably. Does lean like that? Lean does not like that because I'm going to put B and C here. Right, we're going to use this uniqueness thing on BC, and this is going to be HC here. So if we use this uniqueness axiom, then what do we need to prove? We need to prove that B intersects C is not equal to the empty set. And now to prove that something's not equal to the empty set, there, we can use the fact that something's not equal to the empty set if and only if it contains an element. And what element does this contain? It's going to be Y. Let's use Y there. And if we use Y, we now have to prove that Y is in B and C. And both of those are, we have to prove that Y is in B intersect C. So if we split that, that's just, we actually have to prove that Y is in B and Y is in C. And Y is Y and B. Both of those are assumptions. So we can just do assumption here. There. Oops. And now hopefully, great. We've proved, yes, this has worked. Now I just maybe want to, well, maybe this is a good time to stop because there's 1 minute to go. I'm going to spend 1 minute trying to fix my error. I have an error somewhere. And where is it? Does anybody know? Where is my error? Oh, I bet it's here. Is it this? This should maybe be R.2. R.1. Has the error gone away? The error is still there. This proof is fine. This proof is fine. I've made a mistake and I don't know where I've made it. Everything looks fine here. We've defined the two functions. And I just don't, and unfortunately the error message is not helpful. It's not tidy, is it? I'm getting annoyed by my tidy proof. Let's stop using automation. It's not, though, the problem isn't tidy because tidy would have given me an error. This proof is taking too long to compile. So let's do this. Our case is, let's take a block there. No, so rintros. I'm not happy with artificial intelligence. And now it's going to use, and now how do we prove this? Oh, I see. So this is HX and HY there. And now we can now use B, HB, HY, and HX there. Ah, we can't. Oh, because that wasn't the goal. What did I do? Oh, I see. It's this. HY and HX put together. Let's try that. Does it like that? It doesn't like that. Let's use B and HB. Put it like that. It likes that. And now I've got to prove, oh, I see, I've given them the wrong names. I've called them complete. Oh, I see. It's oh, I'm such an idiot. HY. I spelt it wrong. Great. Ah, my error's gone away. Right. So in fact, that's a bug report. So this is a tidy bug. There's some weird bug in the AI I was using. So I guess that's an hour. So I'm going to stop. But the thing I really wanted to show you was, you see here, we've now got to prove, which one is it? Let me just show you what the issue is. At some point, intro P. I don't know what to call it. Intro ZZZ. You see here, I've got to prove that this. That's the easy one. Yeah, that's the. This is the way I wanted to show you. I'll start with this next time. Intro. This is, if I intro P, then the problem here is I've got to prove that two partitions are the same, right? You see this long goal here, I've got to prove that this strange mess here equals P. So how do I prove that two partitions are equal? You see, I've got to prove an equality of structures. And so I should probably use the ext tactic. Let's see what happens if I do that. You see, and that's great. If I use X, okay, wonderful. This is what I wanted to show you, because I made this partition, because I tagged this partition with the X attributes. What have I got to? What does it mean to prove that two partitions are equal? It just means I've got to prove the blocks are equal, right? So let's have a curly collection. There you go. X curly B, and then dsymp. Let's see what this actually needs to be proved. There you go. And now you can see what the problem is. I've got to prove. Oh, this isn't a curly B. This is a normal B. This is just a normal set. I've got to prove that B is a block if and only if B is an equivalence class. You see. So that's some slightly lengthy. I mean, I wonder if tidy can do it. Let's try the automation again. It would be a miracle if tidy did this. I don't think it can possibly do it. Yeah, it failed. So those are the things it got stuck on. Yeah, you see, it didn't know which element to choose. Hard luck. So I'm going to stop there. But in some sense, this was the last thing I wanted to show you. That we introduce a partition. We've got, how do you prove that two partitions are equal? Use extensionality. Two partitions are equal if and only if they're made from the same blocks. So this says there. So let B be a set, then B is a block if and only if B is an equivalence class for the equivalence relation that we made using the partition. Right. Thanks for watching, and I'm out of here.